Hello and welcome to another video. In this video we're going to be working on matrix similarity after acyclic shifts for the weekly contest 373, which was on Saturday. And in this problem you're given a matrix and an integer k, and you have to cyclically right shift odd index rows k times and left shift even index rows k times. Return true if the initial and final matrix are the same, false otherwise. So here they have it here. So we can label these rows as well, 0, 1, 2. So the even row moves left one at a time. So here it is moving left once, and here it is moving left once again, and here it is moving left twice. So essentially every number gets shifted left twice, and they are the same. In the second one, every number is the same. So obviously if you have every row the same, if you move the numbers around, they're still going to be the same. And here we have 1, 2. So if we shift it, it's going to be 2, 1. So here we have a matrix. Just drew this up beforehand, and we're going to figure out like all of our edge cases and where we need to go. So first of all, something we can point out is, so the number of columns here is 4. So let's say our k is like 50. Notice that every 4 movements, we're at the same spot that we were at before, right? Like if we go 1, 2, 3, then we come back here. So every 4 movements, or every length of columns movements, we're back where we started. So what we can do first of all is we can mod k by columns and get, let's say it'll be 2 here, because we don't need to be shifting repeatedly at the same time. We can just figure out like what's the actual final shift. So that's one thing you want to be doing, is you want to take k and mod it by columns, because every time you move number of columns, you're just back where you started. Now for even, we need to move left, and for odd, we need to move right. So we can't actually make like a final matrix. And maybe we can't obviously like move, but it's going to cost us a lot. Like we could make like a deck or something, and for movement we could like pop left and add right or something, right? We can actually have the moves, and then for every 1 in k you can move. But there's an easier way we can handle it. We can just figure out, where did we start? So let's say we started here. Where would we end up? If we want to move left 2, so this is going to be modded by 4. And we're going to have 2 here, right? Because every 4 movements, we're getting to the same spot. So really what we want to move is 2. So if we want to move 2 to the left, we'd move 1 over here and 1 over here. So we'll end up over here. And you can actually do this pretty easily, because Python's kind of convenient. So to move left, all you have to do is, and this would basically handle everything, is you can take your current index and you can just subtract k. And even if we get a negative index, it's fine, because Python supports negative indexing. So in another, let's say you were using another language, I'll talk about that as well, but let's look at the Python one first. So we would get 0, minus 2, and then we get negative 2 as our index. And negative 2 is the second to last element, so it's actually correct. Let's say we wanted to move 3, then we would get negative 3, and then we'd get this index as well, which is also correct, right? It's the third to last element. So you can actually do I minus k. Now, if you don't support negative indexing, let's figure out like what you'd have to do then. So if your language doesn't support negative indexing, what would your calculation be here? And it's also pretty straightforward. So if you think about it, moving left 1 is the same as moving right. So whatever we move left, right? Let's say we move left k equals the same as moving right columns minus k. So let's try that. Like let's say here we want to move left 3. So according to our formula, we'd get 4 minus 3. So we would be here. And that is correct, right? We'd move 1 here, 1 here, 1 here. So there is a way to do it where you always have a positive number. You could just use this as your new index. You could say your new index is just column minus k if you want to move left. Same, we could try this again. So let's say we want 2 here. So we would do 4 minus, we would want to move right 4 minus k, right? So if we want to move right 2, then we would be over here, right? So basically moving left 2, and in this case, moving left 2 and moving right 2 is the same, and that actually is true, right? Like if we move right 2 or we move left 2 is the same. And if k is like 3 and we want to move left 3, then it would be like 1, 2, 3, which would be the same as moving right 1. So it's basically all the same thing. So that's how you would do it if you couldn't handle negative indices. But because we can just take our index and subtract k, and that's going to be our new index. Then we just compare the values, right? So like this, if we want to move left twice, so we get negative 2 here, then we compare these two values, and we know that like this one will end up over here in the matrix once it's actually done moving all the rows. So we can just say like, is this one actually a 1? And if it isn't, then we can return false. Similarly for the 2, we'd check where is it going to end up? It's going to end up over here. So are they the same? No, false, and so on, right? So you basically go every single index, and you just figure out where is it going to end up, and you can compare if they're the same. Because the only way for the matrices to be the same is the value has to be the same as where it's going to end up. Because that's basically what we're going to be doing, right? We're going to make a matrix of all these shifted values, and then we're going to compare if they're the same. So instead of actually moving them, we can just figure out where they're going to end up and compare them in place. So that's going to handle the left. Now let's handle the right. So we can write this as well. So this is going to be odd. Now what about right? Let's say we are at this index and we want to move left. We want to move right twice. Now we can't just add k, right? Because then we'd get 5. So the way to do this, if you want to handle, this is really common, if you want to loop back past a certain index, so let's say like you want to go over here and then you want to loop back to 0. That one is also pretty straightforward. You just do I plus k, and then you mod the whole thing by the number of columns. Because you basically at 4, you want it to move back to 0. So let's see what would happen. If we have a 3 and we move right twice, we get 3 plus 2, we get 5, mod it by 4, and we'd get 1. And that's correct, right? That would be the same thing as moving twice. So from 3, we'd move to 0, and then from 0, we'd move to 1. And you can do that for every single one. So this is going to be the even. And that's basically it. We just have to loop through our matrix, check for every value where is it going to end up, and are those values equal? And if there's ever something not equal, we can just return false. So now we should have enough to code it up. So first, we're going to get the rows and the columns, as always, in most of these problems. Now what we want to do next is we want to simplify k, right? Because if k is bigger than columns, we can just mod it. Because if the number of columns is 4 and k is 50, we don't need to move 50. We can just move 2. So then we just loop through rows and columns. So we'll say like for row in range rows, for call in range calls. So for the odd rows, we want to move right. So if we want to move right, remember, we can just calculate a location. So we could say location equals whatever column we are on plus k. And then remember, we want to mod that whole thing by the number of columns, right? So we ensure that once we're at the last column, we loop back to the start. And we can say if matrix row column, the current one we're on, does not equal where we'll be, matrix row new column or location, and we can return false. And now we have to do the, this is also screwed up tabbing, so let's fix that. Okay. So now the other case is if we have the even rows. So for the even rows, we need to move moving left, right? So to move left, we can say location equals column minus k, and that should handle it for us for Python. But if you wanted to do it the other way, you would say column plus columns minus k, right? And that would be the same thing. So in Python, this is fine. And then we do the same thing. So we can just copy this code. In fact, we can even do this and then just check at the end, right? So we could do this. And that should work. So we're going to move to the right location, and then we're going to check our current thing depending on if we're odd or even. And finally, at the very end, we can return true if we went through our whole thing and it was fine. So let's try that. And it looks good. And there we go. And it's pretty efficient. So let's talk about the time and space for this one. So essentially, we were moving through our entire matrix, which is n by n. These operations are all O of 1. So like this, everything in this for loop is O of 1. So basically our time is n by m. We didn't have to rebuild a new matrix. This is all in place. So it's just O of 1 space, right? We just figured out where the location of the elements is, and we checked there. We didn't rebuild anything new. We didn't, like the worst thing would be probably to make a new matrix and then simulate these k movements. So that's going to be all for this one. And if you did like this one, then please like the video and subscribe to the channel. And I'll make the videos for the next ones in the contest relatively soon. So stay tuned for those. And thanks for watching.